Oh, good morning. This is Pops hanging out here. Got my coffee in. I haven't done anything in here in a while because, frankly, I've been busy, for one thing, and the other one is that both Debbie and I have been kind of going through I don't know what you'd call it. It's not even a cold, but allergies. I don't know. Something hit us. But I figured, what the heck? I'd stop in here and say hello. And at the same time, throw some formulas at you. I haven't been using these lately. That's why every once in a while I go through them just for the fun of it. They're not much. It's stuff that we used to use in the past for guys that were building log splitters, really. What a lot of them were. www.parker, just plain Parker.com. Parker has an entire... Well, I already downloaded it. I don't want to do that again. No, cancel. Where are we here? Download. There it is. Image. There it is. Oh, I've got two of those on here. That's funny. There we are. Get the lighting right. Parker comes up with a whole chart of everything from force to GPM to horsepower calculations to time calculations and gallons per minute, and also cc's to figure out the actual output of a hydraulic pump. There's a bunch of calculations in there for gear pump guesstimates, because they are guesstimates of gear pumps, vane pumps, because you're guesstimating how much of that area is filled up with metal of the gear, but how much is open to the gear teeth or the vanes, but they have some in there that are relatively accurate. The most important one you're going to need to know, got your writing tool down? Ready? I know you can push stop, but whatever. Oh, shoot. I hate to do that because they're going to reflect. But anyway, here we go. The area, say, of a cylinder that's round, most often they're round because that's what holds pressure better. Area equals pi, which is 3.1416. It's infinite, but that's our average. Times the radius of whatever you have. If you got a 4-inch cylinder, the radius is 2 inch from the center of the circle out. Pi times the radius squared. So in our case, I just said 4 inch. Be 3.1416 times 2 squared, which is what? 2 times 2 is 4. But anyway, you get the idea. With 3 times 3, that's not 6. That's 9. So you got to know what you're fumbling with. What's the other one? There's another formula that they taught us that for some reason they thought would be easier. We were taught about pi r squared for years. Area equals the diameter squared. In other words, the diameter, 4 inches, squared, 4 times 4 is 16, times 0.7854. That's like saying 80%, 78%, 79%. Yeah, it did. Move the decimal and you end up with a percent number instead. But anyway, 4 inches, 4 times 4, 16 times 0.7854. That's another one that'll give you the area of that. You say, but I want to know what the volume is. Well, okay, if you do that in inches, measure the length, the travel of that piston in the open area from the back to where the piston deadheads in the back side of the piston. Then you multiply by that. So if it's a 4-inch bore with a 4-inch stroke, that'll give you your figure. So anyway, that would help you there. Another one that we used to do with hydraulics that was interesting was gallons per minute at 1,000 psi. Was a rough guesstimate for electric motor horsepower that was needed. So if you had a 10-gallon minute pump at 1,000 psi, it would take 10 horsepower to reliably give you that. Electric, well, what we found out was in combustion, it's twice that. It is, minimum. So if you have 10 horsepower at 1,000 psi for electric, it's 20 horsepower minimum to maintain your 1,000 psi. Now that's on a standard old full flow pump. That's not variable displacement. Your variable displacements will back off a little bit as the pressure goes up. Usually what they do is they'll stay at 10 gallons a minute and just flow 10 gallons a minute. Maybe I should do it this way. And then when they hit, say, if 2,000 psi is your top setting, they'll start to back off someplace around 750 or 800, depending on how you set the curve. There's usually two adjustments, where it breaks and where it's the final stop. So that's something to consider too. But if you're on a straight gear pump, vane pump, or anything else, you need the horsepower just to plain turn it. So at 2,000 psi, 20 horsepower is probably going to come up short. But it gives you a figure to work with. Now I know on my log splitter, the engine grunts once in a while. I have a pump that was designed for a 5-horse engine, and it's a 2-stage. It shifts around somewhere between 600-700 psi. It'll shift. It starts out at 9 gallons a minute and then cuts off to like 2. I got an 8-horse motor on it. So there's times that thing will blast right through, because I think the actual unloader setting is at about 1,000. So most of my splitting is done and it never shifts. When it does shift, the engine just gives a quick, it actually speeds up. Yeah, because the flow is down. They say, well, what happened to the rest of it? Well, the other 7 gallons a minute. An unloader is not a relief valve. The understanding of an unloader is that the valve pops and acts similar to a relief valve. It does, but the pump is 2-sectioned. It takes one section to the pump, sends it right straight back to reservoir. So the pump itself is continuously pumping with almost no more pressure than it would have had otherwise. So that section of the pump stops. That's it. It just goes back to reservoir, while this section of the pump maintains 1,000 psi plus. It goes right on up to whatever it needs, and this other one just sits here and spins. There's no pressure against it. It's all going off the initial input pressure. This pump has been kicked with a valve back to reservoir until your output pressure reduces below whatever setting it is. So last but not least, not last, there's another one here for conversions. Basic, real basic. You're in your garage, you're working on something metric, and like, dag nabbit, I don't have anything to measure with. Well, 1 millimeter. That's your standard measurement of almost everything we get in the United States. 0.03937 inches. Roughly, if you're doing linear measurements, like you're measuring the length of a rod or a cable or something, it's close enough to start when you're guesstimating, is this the proper adjustment? 40 thousandths, 0.040. It's not quite, it's a little short. So over long distances, anything over a couple of feet, you're going to start getting into variances that you can't make up for. But if you figure you're doing critical engine measurements, this is even a little bit short, but it'll work. 1 millimeter equals 0.03937. We used to have to use that conversion for Deutz tractors 40 years ago, and you could actually rebuild an engine off of that. Then we got used to using the actual millimeters. It made a difference. So what's the other one? 0.1 millimeter? 0.003937. In other words, you're roughly up at 4 thousandths. Just things to consider when you're making your measurements. The smaller, when you keep breaking it down, putting zeros in front of it, it starts getting less critical what that last figure is, that last digit. But still, keep as close as you can, you'll get a good measurement. And last but not least, electrical circuits. Volts equals amps times ohms. In other words, your voltage equals the amperage that's flowing times the resistance. So V equals AR. And that one you can divide and come up with all kinds of other calculations for your electrical. Those are the major ones that you need to use when you're out there in the field or in the shop. But usually it gets used in the field more than anywhere else. This is Pop signing off.